All right, I want to go through this problem just in case we don't have enough class time. We have mass 1 on top of mass 2, and here it shows us the coefficients of friction just labeled as static 1 and kinetic 1. And then there's a different coefficient of friction between block 2 and the surface. So we have to be careful with our subscripts here. In this situation, we have, it's defined down here, that the mass for big M is small enough that the entire system remains at rest. Okay. We want to label the force, draw the force vector on the block, as well as determine the magnitude. All right, so let's look at block 1. Block 1, it's asking for the value of the normal force. So on block 1, the normal force is going up, and block 1 is acting just as if it's sitting on a flat surface. Now, be careful because on a problem like this, it's simply asking you to draw the vector for the value that they want you to find. So you would not include the vector mg. However, we have to think about all of those forces. So we know we have the normal force up, we have mg going down, and the object is not accelerating in that y direction. So what we get is that the normal force equals mg. And it's important for this type of problem that it did specify what the answers could be given in. So it says you have to answer it in terms of the masses, the coefficients of friction, and g. That's it. You can have the m's with their subscripts, the mu's with their subscripts, and g in the responses. So for this one, we just have m and g, we're good. And I got to subscript that as mass 1. All right, for block 2, they want us to know the friction acting on block 1 from block 2, so between those two surfaces. Now, since the objects are at rest, block 1 is just acting like it's sitting on a flat surface. So here, you wouldn't draw any vector, and you would say that the friction on object 1 is 0. Now we look at the tension on block 2. It's going to the right. And this system is not accelerating. So we have to figure out what the value of tension is because we're not allowed to have T as our final answer. We can only have M's, G's, and Mu's. So we have to think beyond this. We have the big mass with a force of gravity pulling on it, and we have the tension going up. And that tension is the same everywhere within the chord. So this is where block 1 and 2 are. So the tension here that we're looking for this problem is the same as the tension up on this block, big M. Now, since big M is not accelerating up or down, the tension has to equal mg, big mg. So that's our answer for part 3 here. And now the normal force on block 2 by the tabletop. Normal forces are going to act up on the surface. Now that value has to equal the total force downward on the table. The total force down is the weight of block 2 plus the weight of block 1. So that's what the normal force on block 2 is going to be. next step is the frictional force on block 2. So block 2 is not sliding, so it's holding the object back, and that's frictional force 2. However, what else is acting on that block is the tension is pulling it to the right. So if that object is not accelerating, we have the tension to the right minus friction 2 equals 0. Again, that shows us that tension equals friction 2, but we can't have tension. So we look back and we see that the tension equals big mg. Okay, now part B. What is the largest value of m so that the whole system remains at rest? So if we take out all of the internal forces, now we can go about finding our equation by writing up all the individual equations of each of the blocks and combining them together. However, nothing is accelerating, and the only force that would cause it to move is big mg, and it's not moving because there's friction acting backwards on block 1 and block 2. So tension here, friction there, big M with big mg going down, tension going up. So the internal forces are the tensions. We can get rid of those. So our equation for the system is going to be big mg minus the frictional force equals 0. But we can't have a frictional force symbol in our equation. So we have to substitute in for what the frictional force is going to equal. And since this is 0, mg equals the frictional force. Now the frictional force equals the fun equation. And for this one, it's static, and for object 2, because it's the block on the surface, times the normal force. But we can't have normal force in our answer. So mg equals mu s2, and the normal force acting on the two blocks stacked together is m1 plus m2 fix that up times g. Hopefully that's in the video. And then the g's cancel on each side, so that the answer is big M is mu static 2 m1 plus m2. This is a mu. Doesn't look like it. Okay, for the next part, we have the system accelerating. However, there's no slipping between the two blocks. So that means that block 1 and block 2 are acting just like one larger object. So it's like they're glued together. So we have mass 1 and 2, big mass, and we still have that friction happening here. However, it's sliding now, so we have to use the kinetic frictions. All right, those are our external forces, big mg, and then the kinetic friction acting on the blocks. The tensions will cancel. If we write out all of our equations and add them together, you would see that. But I'm going to skip it for this one. I need to do it on the next couple. So the net equation is big mg minus the kinetic friction 2, and that's going to equal MA. But the MA is going to be the total mass of the system that is accelerating. So we have big mass accelerating, we have mass 1 accelerating, and we have mass 2, all with the same acceleration. All right, so we can have the M's and the G's in there, but we can't have the F, so we have to make the substitution there. So that big mg is equal to, this is going to be mu K2 times the normal force on the 2 blocks stack, and we've done that a couple times already. That's going to be mass 1 plus mass 2 times g, and then that equals all the masses added together. All times A. All right, so I'm going to basically open another page and write out the final solution. I'm sure you guys can see what's happening. You just divide both sides by the sum of the masses. All right, here's our final response. All m's, g's, and mu's. And that would be the acceleration of the entire system if M1 does not slip. All right, the next couple questions are a little bit tougher. All right, so now it's accelerating so that mass 1 is slipping on mass 2. So if we are able to kind of look at them, mass 1 would kind of be sliding back. Actually, they're both going to be, mass 1 and mass 2 are both going to be moving forward, except mass 2 is going to be moving underneath mass 1. So eventually mass 1 should fall off of mass 2 as it slides off the back. So let's try to draw some force diagrams. So this dot right here is going to be mass 1. Mass 1 has gravity pulling down, the normal force going up. The normal force is going to be equal to its weight, so it's m1g. And it's moving forward due to a force, and that force is, if m2 is trying to slide forward, and it's the friction between them is what brings the mass 1 along with it. So that the frictional force is actually what causes it to accelerate. For mass 2, we have the total downward force, which is mass 1 plus mass 2. Keep doing that. Times gravity. We have the same amount of force upwards, mass 1 plus mass 2 times gravity. Here we have the tension pulling it forwards, and we have the friction from the surface, but also the friction from block 1, mass 1, pulling back. So since between the block of mass 1 and mass 2, the friction between those is pulling this one forward, the third law says that there must be an equal and opposite force. So if mass 2 is pulling forward on mass 1 is pulling backwards on mass 2. And lastly, block big M has big mg going down, and then tension going up. If you don't catch that there's two frictions and the third law acting on that second mass, you just got the rest of the problem wrong. So you really have to think about why the motion is happening. All of the interactions, always think about what are the forces that are basically being created from the interactions between all the objects in the system. So here we're looking at we want the acceleration of block 1. So let's just look at object 1. We have the friction causing mass 1 to accelerate. And that's it. This one's actually pretty simple. This one's a little bit tougher. We're going to need all those diagrams for the second part. So since the frictional force is the only thing causing this mass to accelerate, that frictional force is equal to mu 1k times the normal force acting on it, which is m1g. That's going to equal m1a. And you can see that the m's cancel, and we're left with the acceleration is equal to mu 1k, k1 times g. That's it. So that's not too bad. All right, for the next one, we have to combine all our equations. Well, not all of them, actually. We have to combine big M with M2. Right? So here's our equation for M2. We have the tension going to the right. We have friction 1 to the left and friction 2 to the left. And that's going to cause mass 2 to accelerate. On big M, we have big mg minus the tension. It's going to cause big M to accelerate. Now when we add those two equations together, the tensions cancel out. So we're going to have big mg minus friction 1. Now friction 1 is equal to mu k1 times mass 1 times gravity. All right, so that's friction 1 minus friction 2, which is mu k2, times the normal force acting on it, which is mass 1 plus mass 2, times gravity. And that has to equal the sum of the masses. So the big mass and M2 are accelerating at the same rate. Mass 1 is accelerating at a different rate. So you cannot combine that with those other two objects for this situation. But we got rid of all other variables. We just have to divide both sides by big M plus M2. And that's what the acceleration is going to be. That's the problem. All right, hopefully you're able to follow along with that. If you have any questions, please bring them up. But there is the only type of open-ended problem that we could probably do up to this point. All right, everything else contains multiple chapters together and things that we haven't seen yet. All right, so that's it.